Hello, everybody. So what we're going to be looking at today is the second part of our lecture on cross products. So last time we just kind of stopped because we made it to about an hour without finishing the topic, and it looked to me like there was quite a bit left. So where we left off was we had calculated cross products using the determinant definition, but we hadn't done any applications, and we hadn't talked about any kind of geometric implications of the cross product, right? So what do we need? Let's write this down to start with here. So let's just recall that if you have, let u equal, u1, u2, u3, and v equals v1, v2, v3, then we have the cross product, which we know how to calculate, u cross v. And the way we calculate it is with the determinant of a 3 by 3 matrix, right? IJK on top, then you put your u, and then you put your v. Now, I'm sure we mentioned the last time that this operation is not commutative, which means that the order here matters, right? So if the order here matters, then you have to make sure that the top row, not top row, but the middle row here is u, and the bottom row is the v. And if you get that backwards, that's equivalent to reversing these two things, which actually makes your answer wrong, right? So we have that. And also from the previous lecture, at some point, we talked about how the magnitude, oops, let me get the pen tool. The magnitude of u cross v was magnitude u, magnitude v, and then times the sine of the angle between them. Okay, and we'll use both of those now. So let's let us get started here. So what we want to do is talk about the geometric interpretation of this. So geometric stuff using the cross product. So where we start with this is we're going to consider a parallelogram. So consider the parallelogram. Parallelogram. Okay, what's a parallelogram? So a parallelogram is a shape with two sets of parallel sides. So like, put one there. Oh wait, well yeah, that's fine. Put one over here. It's parallel, and let's put a line here, and let's put a line here. Okay, so you'll notice that two of those sides I labeled as vectors. So I called this one u, and I called this one v. So we're looking at a parallelogram here, okay? And, probably you don't remember this. There's not a lot of opportunity to use this, but the area of a parallelogram is simply the base times the height, okay? So the area is base times height, right? Same as a rectangle. So the base times the height. Okay, now the base, of course, is just going to be this bottom side here. What's the height of a parallelogram? Well, the height is you have to measure from the base at a right angle up to the top side here. That's how you measure the height. So you could measure the height here, for example. That would be the height. And the thing about the height is that you can calculate the height here in terms of this angle. So if you stick this angle theta here, then it turns out that this side of this little triangle would be computed as magnitude v. I'm going to change this real quick, by the way, in a second here. I'm switching the labeling on the sides. Magnitude v times sine theta. That's wrong at the moment. That's a lie. And I'm changing these variables to match what we have in the book. Sorry about that. So let's call this one V, and let's call this one U. Okay. So if you label them that way, then you can calculate this side of the triangle from this side of the triangle. And it's calculated this way, magnitude V sine theta. Okay. But what that means then is that you can write the area in terms of the vectors that you see here, right? So in terms of U and V, U and V, we see that the area it's the base, right? But this is the base. So the base is the vector U, right? U. So the base is the vector U. So if you want the length of that, the length of the base is simply the magnitude of U, right? That's your base. Now, if you want the height, well, we just put the height right here. It's magnitude V sine theta. Like that. So that's just from the picture that we've drawn. But then if you look at what you've got here, you've got magnitude U, magnitude V times the sine of theta. And you know from the previous lecture that magnitude U, magnitude V sine theta is the magnitude of the cross product here. So right away, we're able to say that this area is actually the magnitude of U cross V. Okay, so that's a derivation of the area of not a derivation of the area of a parallelogram. That's the wrong way to say that. What that is it's showing you that the area of a parallelogram, which is base times height, also just manages to be the magnitude of U cross V, where the two sides are being interpreted as vectors. Okay, so that's a formula. So what can we say about that? Well, I want to write it out kind of, a little more carefully than we have. So we'll say definition, or theorem, I guess is what they call it, not a definition. Theorem, area of a parallelogram. And they say if we locate vectors U and V such that they form adjacent sides of a parallelogram, I have to write that, such that they form adjacent sides of a parallelogram, then the area of the parallelogram is what we just wrote. So area equals the magnitude of U cross V. So there you go. And of course the picture is right up there, so I'm not going to draw another picture for it. So that's just a thing that, people remember. Okay, and basically what we did right above that was the proof of that theorem. Also, just kind of a corollary here is corollary just means a theorem that is trivial. If you know one theorem, then a theorem that you get from that theorem with no work really is called a corollary. So that says coro. Oh, I can't write word. Where's the eraser? Corollary. The triangle, right? If you go here, call that U. You go here, call that V, right? This triangle has area 1/2 magnitude U cross V. And the reason why is obvious if you draw just a couple extra lines in here, right? Just imagine you did this, right? You've got this parallelogram that is the magnitude of u cross v. And so this triangle that's just u on one side, v on the other side, that's obviously half of the parallelogram. So the area is half of the parallelogram. Okay, so that's just something you get for free. So we call that a corollary. Okay, awesome. So something that we haven't done is we haven't really done cross products where the vectors were not given to you. And so I definitely need to do an example of that. And so here is a good example. So find the area of parallelogram PQRS with vertices P110, Q710, R942, S342. Okay. So, I mean, it is what it is here. You can't really draw, well, you could, but it's hard to draw things in three-dimensional space. And so I'm not really going to do that. I'm just going to go P, Q, R, oops, not going to be, yes. And you can just double check that this actually makes sense. You have to be careful that you're not getting one of the diagonals here. Um, so let me think. So P and Q are on one side, R and S should be on the other side. Actually, hold on a second here. Yeah, I guess P to Q to R to S. It must be right. They wouldn't say PQRS if that was wrong. They would have put them in a different order. Okay, so let's just say that that's our parallelogram. All right, so if that's our parallelogram and we need to calculate the area, right? That's what we're trying to do, find the area of the parallelogram. And the thing is that we're not given any vectors. So that's kind of the thing that you have to deal with here. So notice you have 0 vectors given. So you actually have to figure out what the vectors are before you start. So step 1 is to figure out the vectors you need. Okay, so hopefully that makes sense, right? Because if you're going to be doing this calculation up here, you need the u and the v, right? The vector on this side and the vector on this side. So you got to figure them out. We don't have them, right? So what you do is just label the vectors that you need, and then you can calculate them. So we should, so start by computing what? Well, what you do is you just do this. Put a vector there. What vector is it? Well, it goes from P to Q. So that's vector PQ. And then we need the other vector, right? So we're going to need PQ. And also we're going to need this vector, PS. And, you know, those weren't the only 2 choices that we had, but the thing is basically that they need to be going from the same point. So PQ, PS, or you could have used like SPSR, or you could have used RSRQ, or you could use QRQP, right? But the point is that they start from the same point. And those are the ones you need, which is why I stopped to think for a second about whether or not it actually was from P to Q to R to S back to P. And then I decided that it must be, just because they wouldn't have said P, Q, R, S. Like, you use that kind of language when you mean from P to Q to R to S, back around to the start. So, and I did that because I wasn't going to graph these in 3D space properly because I'm lazy. Okay. So you have to start by actually computing these vectors, and then you can just do the cross product. All right, so let us get going. So we need PQ. So how do you form the vector PQ? Right, you have to remember back to the original lecture we did on vectors. So when you're doing PQ, you subtract the components of Q. You do the components of Q minus the components of P, right? Terminal point, initial point. So you go 7 minus 1, 7 minus 1 for the first component, 1 minus 1 for the second component, 0 minus 0 for the third component. Right? So you actually get 6, 0, 0. Well, that's nice. We need the PS. Same thing, but this time we're doing S to P. So components of S minus the components of P. So S minus 1, 3 minus 1, 4 minus 1, and 2 minus 0, I think. So what do we get? We get 2, 3, 2. Yeah. Okay. So you've got those vectors. And then now that you have the vectors, then we can calculate the area using the cross product. So now we can compute the area using the magnitude of the cross product. All right. Now, going back to what we know here, it's initially easy to get confused about stuff when you're doing this, right? So the thing that we actually care about is this, the magnitude of the cross product, right? So you might be, what's the word? Tempted? You might be tempted to try to use this formula. But the problem with using this formula is the magnitude of U, or in our case, PQ, is easy to get. The magnitude of V, or PS, is easy to get. But where does the sine of theta come from? You don't know the theta, so this is not what you're supposed to use. Okay, what we're actually going to do is we're going to use this top formula, actually calculate the, we're actually going to just calculate the cross product, and then we're going to calculate the magnitude using the normal magnitude of a vector formula, right? So don't use this because we don't know theta, right? If they told you theta on your picture, right? If you had a theta here, then you could use the magnitude U magnitude V sine theta formula, but we do not know it. Okay, so we compute the area from the magnitude of the cross product. So first compute the cross product. So we're going to compute PQ cross PS, which is, trying to make a straight line there, I, J, K, those are vectors. Then we put PQ, which is 600. And then we put PS, which is 232. Then we have to remember how to compute the determinant of a 3 by 3, which we covered last time. So it's going to be I, and then a 2 by 2, which is 0032. Then minus J, don't forget the minus. We're going to have a 2 by 2, 6022. If that's confusing to you, go back and look at the previous lecture where we talked about determinants of 3 by 3s. All right, K. So we got 6023, like that. So there is our cross product. We need to finish it up. So we have I, parentheses, 0 minus 0, okay, 0, minus j, parentheses. We're going to have 6 times 2 is 12. 12 minus 0 is just 12. Plus k. 6 times 3 is 18. 18 minus 0. So just 18. So what do we get for our vector? Well, we just get minus 12j plus 18k, if you want to write it that way. Or, right, there's no I, so we don't even write the I. Or if you use the triangular bracket notation that I would prefer, I get 0, negative 12, negative 12, comma 18. That's how I'll write it. Okay, so we have our cross product. Now, what are we going to do with that cross product? We're going to calculate the magnitude to get the area. So the area of the parallelogram is going to be the magnitude of that vector, which we know how to do. It's the square root of 0 squared, 12 squared, 18 squared, right? And as always, when I do these, I just throw away the minus signs to make it less writing, because I know it's going to be positive anyway, right? So 12 squared, of course, is 144, but I have no idea what 18 squared is. The total is 468, so we get square root 468, like that. And then, of course, we need to square root that. So you use a calculator or Wolfram Alpha or something that can give you an exact answer here. So this is 6 square root 13. And that's actually what you want. And if you wanted to round it, of course, we can get a fraction to decimal. So that's approximately 21.63. Okay. So that is what it is. And yeah, we did it. So we calculated the area of a parallelogram now. Okay. So now we're going to move on, and we're going to talk about triple scalar products, which also have something to do with geometry. But first, we're going to talk about what the triple scalar product is. You've seen it once, but only momentarily. It was just listed in the list of properties, I think. Triple scalar product. So what is a triple scalar product? So the triple scalar product of U, V, W is U dot V cross W. Okay, and that's not a like, oh, why is the triple scalar product that? Right? It's not something like that. The triple scalar product is U dot V cross W because, I mean, that's our definition, right? This is our definition of what the triple scalar product is. So triple scalar product, this thing, this thing. That's just what it is by definition. Okay, now we haven't talked about why we would care. Where is, they're not giving me the identities. Oh, that's super annoying. Oh well. Yeah, I guess they only give you this one. The only identity they give you is that this is also equal to U cross V dot W, if you want. So why would it be that? I mean, I don't really know. But there's others. I think there's 3 of them that are equal. I think, don't quote me on this. Well, I mean, I guess I'm recording it. But I'm pretty sure that the way it works is kind of like the U, the V, and the W. I think you can probably change the positions of them. But you have to keep them in order. When I say keep them in order, remember when we did that thing with the IJK? I think they have to be in order like that. Like you could like slide the U over to the V position, the V over to the W position, and then the W would come back to the beginning and be here. So you'd have a W here. That's this W. So you'd have a W here, and this would be U and V. So that's the U and V, that's the W. And you say, well, why is it at the end instead of the beginning? But you have to remember that with dot products, because this is a dot product, it doesn't matter the order. So if you move the U over one spot like that, and then you move the V over one spot, and then the W went back to the beginning, that gives you this. And I think you can just keep doing that. So if you move them over one more time, you get something that's also the same quantity. But if you did something like this, if you switched the order of two, why can't I write? If you switch the order of two, then you actually change the sign, and that's bad. Okay, so it doesn't really matter. The point is this is the triple scalar product. And the thing about the triple scalar product is you could calculate it just from calculate V cross W and then do the dot product with U, right? If you were given three vectors, you could do the V cross W first and then the dot product. But the thing is that you don't have to. There's kind of a shortcut. And the shortcut is this. I'm just trying to scroll to where it is. Don't really need it, but we can do it. So kind of the way you can calculate this in easy way, quotes, easy way to compute the scalar product, triple scalar product, is with another determinant. So we want U dot V cross W. And it turns out that what you can do is you can use the determinant for the cross product, right? Normally, like if you covered up the U and you say like, what would this cross product be, right? And it would be I, J, K. And then you would have like V1, V2, V3, and then you would have W1, W2, W3, right? But if you add this extra U there, it turns out that what you do is just, if you erase this top part and you put U1, U2, U3, these are V's. Then that's the triple scalar product. And the reason it works is pretty easy to see. If you think about it, when you do the dot product, of another vector, right? Like if you went like this, like U1, U2, U3, you were going to do that dot product. You would multiply the U1 times that zero, right? The U2 times the middle term, and the U3 times the third term. But if you come back up here, if you just replace this with the U1, this is the first term, right? So just replace this I with U1, replace the J with U2, replace the K with U3, and that's actually going to be the same thing as what your dot product is. So rather than waiting to the end, you can just replace this with U1, U2, U3, and it just magically works out. Okay. So that's how you can compute the triple scalar product in, a relatively simple way. Let's do an example of that. It's just less work to do it that way. So let U equal 135. V is 2, -1, 0. W is -3, 0, -1. And we want to compute the triple scalar product, U dot V cross W. So it's going to be a number, right? Because a dot product always gives you a number. Let's do this. So it turns out that this is going to be U dot V cross W. Everything in Calculus 3 takes longer to calculate than you think, just because of the amount of writing that you have to do. Oops. scalar product. So you put u in the top row, right? So top row is going to be 1, 3, 5. Middle row is v, 2, -1, 0. Bottom row is -3, 0, -1, the w. And there you go. So you can remember how to do a determinant. We're expanding along the top row again. So, right, start with the 1. So you start with 1 instead of I, and then a 2 by 2, -1, 0, 0, -1. Then the middle one, we got a -3. Don't forget the minus here on the middle term. And then a 2 by 2, which is going to be 2, 0, like 2, -3, 0, and -1. 2, -3, 0, -1. And then finally plus the 5 for the, come on, erase. Cover up the row and column there, and you get 2 by 2, 2, -1, -3, 0. So we just calculate this out. We have 1 parentheses. -1 times 1 is 1. 1 minus 0. 1 minus 3 parentheses. 2 times -1 is -2. -2 minus 0 again. We love zeros in these. Plus 5 parentheses. 2 times 0 is 0. 0 minus 3. 0 minus 3, which is -3. So what do we get? We get 1 plus 6 minus 15. Is that right? Hopefully I did not make a sign error. It is really easy to do that. What are we going to get? 7 minus 15. Is that -8? Probably. Okay. As always, you have a number of computational tools you can use to cheat. We'll go to Wolfram Alpha, good friend, Wolfram Alpha. And probably the way you would type this in is we're trying to calculate the determinant of a 3 by 3 here. So I would just go det for determinant. And there's lots of ways to type in a determinant where it would understand. It likes curly braces, but I'm too lazy to type curly braces in. So use parentheses 1, 3, 5, close parentheses, comma, 2, -1, 0, parentheses, comma, open parentheses, -3, 0, -1, close parentheses, close parentheses. Now you'll know if you did it right, or you'll know if you did it right enough if it does what you want it to do. Yep. So it did this determinant, and the result is in fact -8. So not too bad there. So that is how to calculate a triple scalar product with a 3 by 3 determinant. Not that much work. A lot of graphing calculators can do determinants of matrices, but you know, by the time you type in your matrix, you probably could have solved it by hand. So yeah, that's about it. Let us see here. We did a triple scalar product. I don't want to do another triple scalar product. Okay, there we go. Yeah, so it turns out that if you make another shape, so we did area of a parallelogram. Now we're going to do volume of a parallelepiped. That's not even close to parallel. Okay, put L's. Parallelepiped. Awesome. What is a parallelepiped? So a parallelepiped is sort of like a cube, but that's been, instead of the sides being rectangles, they're parallelograms. So it's just like a squished cube. I want to draw it pretty straight up and down just because of drawing. So like you got a side and then okay, there we go. That's a parallelepiped. So it's like a cube just been tilted a little bit, squished. But what you've got here is three vectors. So you've got this side here, which you could call u, and you got side here that you could call v, and the third side, I didn't draw the third side. Let me draw third side. So oh man, hold on. There, there, there. Okay, there we go. So your third side is going to be here, right? And that's going to be w. So those are your three vectors that you would need to determine a parallelepiped in the same way you do a parallelogram. And it turns out that the volume of that is going to be the triple scalar product. Okay. So let us write that. So the volume, I'm going to sort of be cheaty here and just to say it faster. The volume of the parallelepiped, I'm just going to say determined by u and v and w, u, v, and w, just so I don't have to write like adjacent edges, blah, blah, blah. And it's not quite the triple scalar product. It's the absolute value of the triple scalar product, because if you go back up here, like we just saw, you do a triple scalar product, the result might be negative, and the volume of something is not negative. So, and you know that also with a v and a w, switching the order here changes the sign. So rather than worry about putting these in the right order, we can just say, well, take the absolute value and that'll be the right answer, rather than worrying about the right order to get a positive number. All right, so the volume of the parallelepiped determined by u, v, and w is the absolute value of the triple scalar product. Write it. Area, nope, that's called a volume. That's called a volume. Volume is equal to absolute value of u dot v cross w. And also notice that I'm using absolute value. So there's only one vertical line, not two, because 2 means magnitude of a vector. But this result is a scalar because v cross w is a vector, and then a vector dot product with another vector, the dot product gives you a real number. So this is a real number, and we're just taking the absolute value of it. There are some math classes where you do double lines for real numbers, but that would generally mean that you're not using the regular absolute value, you're using another mathematical operation as sort of a stand-in for absolute value. Pretty advanced math before you start doing that though. So don't, not for us here. Okay. Let's do one of these. So let's just make up our own here. We could use the books. Let's make up our own. So let's see if we can draw some vectors. I don't know if I can. All right, so this has got to be X. This has got to be Y. This has got to be Z. So let's just pick a couple of vectors. They can be anywhere we want. So let's say we do this. So let's take one of them on the back here. So like, let's go like that. And I guess that looks like, that vector to me looks like I did 0 in the x direction, 2 in the y, 2 in the z. So that's the vector 0, 2, 2. So I'm drawing it like on the back wall, basically. Okay. And let's say we're going to do another vector. Let's make it come out at us. Let me get a color that we can see. So from there, let's come out this way. And let's say that that vector is going to be, what would that vector be? I mean, it could be anything, but it's just in the x direction. So let's just say 3, 0, 0. That one. And we need a third vector to make a parallelepiped. I don't know if I'm going to be able to draw the resulting parallelepiped. I think I drew them in a bad place. But this is what we have. So let us go on the bottom here, like this. And that's in the y direction. So let's call it 0 in the x. Let's call it 3. We're going to call it 3 in the y. And 0 in the z. Okay. Now, what would that parallelepiped look like? Well, it's a little bit hard to see, but so I'm going to redraw it over here where I can draw it a little bigger. So like that or something. So anyway, what you would do is you would say, okay, well, get a gray or something. This is one wall. And then in the bottom here, you've got one like this. And then on the top, you've got one parallel to the one that we already drew. And then on the top, you've got that. So it's not really like some shape like this drawn over here would be the parallelepiped that we're doing. But we can calculate the volume of that with a triple scalar product. And it's just the absolute value of the triple scalar product. So you just go, well, we know that the volume is simply U dot V cross W, but then absolute value to deal with the fact that it could be negative. And because of the absolute value, the order that we put anything in doesn't matter at all. So we just put the 3 vectors in this matrix in any particular way. So I can just go like 0, 2, 2 on the top, 3, 0, 0 in the middle, and then 0, 3, 0 in the denominator. Now you can actually save yourself some work if you put the one with the most zeros on top. So like I could put, if I switch these two, it'll be less work and you'll see why. So like I could put 3, 0, 0 and then 0, 2, 2. That'll be less work. Also, we still need the absolute value of this, which is a little bit weird notationally. All right, so absolute value. So like if you expand along the top row here, right, you get 3. So you get 3 and then a 2 by 2. And the 2 by 2 is 2, 2, 3, 0. But then you get minus 0 and then a 2 by 2 when you expand along, or when you take that one, right? So you end up with 0, 2, 0, 0. And then your last one, you have plus 0 and then 0, 2, 0, 3. Now, the reason I wrote them all out, though, but you don't really need to because just think about it, right? This is going to be 0. This whole thing's going to be 0, and this whole thing's going to be 0. So we like zeros in here, right? It's nice to have those. I wanted a different color, pink. Zeros here make this easier, right? Because what we're going to get here is going to simply be this is gone, And so we really only have one of these to deal with. And so it's simply going to be the absolute value of 3. And then here we got 2 times 0, 2 times 0 minus 6. So we're just going to get 18. So the volume of the parallelepiped is 18 cubic units, right? It's a volume, so we're measuring in cubic units. So the volume is 18, and you just write like units cubed. Okay, so that's useful geometry calculations here. All right. So there are some applications of the cross product that involve torque, and I'm not going to cover them because we could cover them later if we need to, and also you can cover them in your physics class if you care. So don't want to do too much physics in here. We are a math class and we have enough to do on our own. So I'm going to call that it for this semester. I wish I could, right? That's it for this semester. Hope you had a good week. See you in the next class. Now, I'm going to call that it for this lecture. And yeah, see you in the next lecture when we're going to talk about lines and planes. That's it for now.